There were lots of confusions. So the first thing was that what is the fundamental domain for gamma p, the Fuchsian group for pair of bands. So the fundamental domain is what I have drawn here. So the domain contains a part from the real axis, and if so you can see that near the real axis you are actually realizing a hyperbolic annulus, and then if you want to get a pair of bands with boundaries having finite length, then you are supposed to provide a cutting rule. You are supposed to cut the fundamental domain along a geodesic that connects two adjacent sides with minimum length. So that was one confusion. And then the second confusion was that I said when I was trying to define the Teichmuller space for Fuchsian model, I said we have to start from upper half plane and then consider all possible quasi-conformal transformation. But I think when I wrote it, I think I wrote, but I didn't emphasize the fact that I'm not supposed to use all possible quasi-conform Beltrami differentials or quasi-conformal transformation. I'm supposed to use only those Beltrami differential for computing a quasi-conformal transformation, a Beltrami differential that has the periodicity property. So it should be transforming like a differential form with -1 degree under the Fuchsian identification. So if I start with a Beltrami differential mu c, then I can act with an element of gamma of the Fuchsian group. Then after once you act that, then you should produce mu c, then multiply it with d gamma c divided by dc by the complex conjugate of d gamma c divided by dc. Only if you have this periodicity condition, you can use them to deform the Fuchsian group and then get a new Fuchsian group. So you can see that here you have a Beltrami differential. Effectively, this is a differential that is defined on a Riemann surface. Now a Beltrami differential defined on a Riemann surface will provide you a quasi-conformal transformation which may or may not change the complex structure.
Is the differential defined on the Riemann surface obtained by modding out with gamma?
Exactly. Yeah. So
first choose a group gamma.
Exactly. First choose a.
Then look for all these quasi-conformal transformations that satisfy this property.
Exactly.
Is a finite number of them?
Or
an infinite number?
Yeah, it should be infinite number of possibilities.
Up to equivalence with purely conformal is finite or infinite?
Oh, the dimensionality is finite.
Yeah, so the number of parameters is finite.
Is finite, right?
Is the number of parameters the same as the number of parameters in space of complex structures?
Yeah.
Right.
Yeah. So that's exactly equal to the number of the dimensionality of Teichmuller space.
Right.
So some. Yeah. That is true. Yeah. So in that sense, the example that Shiraz was trying to make suggests so he suggested a quasi-conformal transformation f of c equal to c plus epsilon c minus c bar. So you can compute the Beltrami differential, which is just minus epsilon divided by 1 plus epsilon. So you can see that it's a constant which has not much of periodicity. So this is periodic only under, or this particular Beltrami differential transform as a differential form only under translational group. So it's not invariant under full Fuchsian group. So that's why you can't expect a quasi-conformal transformation like this to change a Fuchsian group to another Fuchsian group. So that was the main confusion, I think.
Can we also show that using such things, gamma will go to, there was confusion about getting SL to Q.
Yeah. So what I could do is that maybe a direct argument on the upper half plane or the complex plane, to me it looks slightly difficult. At least I don't see it immediately. But one way to think about this is that anyway you are obtaining this quasi-conformal transformation from a Beltrami differential that is defined on a Riemann surface. So this quasi-conformal transformation is going to change the complex structure of the Riemann surface. In that way, you are obtaining a new Riemann surface with a different complex structure, and then you can again use the uniformization theorem. So there is a corresponding Fuchsian group. So you go from Fuchsian group, go to Riemann surface, and then deform the Riemann surface, and then you have a modified Fuchsian group. So you could think of the first map as taking gamma to gamma tilde. So, but there should be a direct argument on the complex plane itself. Somehow I don't see it immediately. So I promise that all this abstract discussion can lead us to something explicit. So that's what I'm going to do today. So we found that the Beltrami differential, all possible Beltrami differentials having the periodicity property is not going to give you different Riemann surfaces. There are some variation along the space of Beltrami differential that won't change the complex structure. So those are the null vectors. So we wanted to identify which one is null vector and which one is a genuine vector, which can vary the complex structure. So for that, we found a filtering process. So the process is that you have to start from a Beltrami differential that is defined on the upper half plane, and this is a Beltrami differential that belongs to the space of all possible Beltrami differentials that transforms under the Fuchsian model gamma. And then, so this is here we define the differential on the upper half plane. Now we extend the Beltrami differential to the lower half plane by saying that you have a new Beltrami differential mu tilde c, and then that is defined as mu c, where c belongs to upper half plane, and 0 for c belongs to lower half plane and real axis. So now the idea is to compute the quasi-conformal transformation that has this Beltrami differential omega w mu tilde. This is the quasi-conformal transformation defined on a complex plane, not just on the upper half plane. So you should solve for this Beltrami differential and find a quasi-conformal transformation on the full complex plane. And then we can take the Schwarzian derivative with respect to.
This is the canonical thing, right, on the upper half.
Yeah, so when I demand that omega mu tilde c satisfy these normalizations, then that's the canonical quasi-conformal transformation, and this is what we are supposed to use. And then we can take this canonical quasi-conformal transformation and then put it into the Schwarzian bracket. So that provides us a quadratic Beltrami, a quadratic differential on the complex plane,
So,
or on the lower half plane.
These canonical conditions, there is a one-to-one match between the Beltrami differentials
And the quasi-conformal transformation.
So
Yeah.
then there is a one-to-one correspondence between the quadratic differential and the
Yeah, so that's why, yeah. So there it's actually not one to one, it's actually many to one.
because of the Gaussian
Yeah.
being negated from the sign.
Not just because of that, it's because of the theorem that I stated, which I didn't properly explain. So I said that if I can define an extended Beltrami differential and then compute the quasi-conformal transformation on the whole complex plane, then I said that this particular Beltrami differential mu tilde, whether that's going to change the complex structure of the Riemann surface or not. So the characterization was that if the function omega mu tilde and some another quasi-conformal transformation omega nu tilde with Beltrami differential nu tilde, so the idea is to see how mu tilde and nu tilde is going to change the complex structure. Are they going to change the complex structure in the same way or not? So if omega mu tilde is equal to omega nu tilde in the lower half plane, then we said that that's not going to change the complex structure of the on the real axis. If it is equal on the real axis, then it is also true that it is equal in the lower half plane. So this was the equivalence relation. So since we are computing the quasi-conformal transformation on the lower half plane, the Schwarzian will provide me a one-to-one map to complex structure and the quadratic differentials. So here C belongs to H star. So this was the, so all such possibilities provide you this space A2 H star gamma, and then we identified this space with the space of quadratic differentials defined on the lower half plane to the Teichmuller space of Fuchsian model.
But also there is a step here, right? Because this quadratic differential, because I guess mu respects the gamma, this will also respect gamma. So it
Exactly. So that's why I claim that this is quadratic differential. Yeah, because of the transformation property which is induced from mu tilde is the one that is making phi mu a quadratic differential. The Schwarzian derivative f of c is defined as d cube of f of dc cube divided by df dc and then minus 3 by 2 I think d square f dc square divided by df dc whole square. So one can take the Schwarzian derivative and then obtain a quadratic differential. Then from there we get the filtering process, that you can inverse the relation between Beltrami differentials and the quadratic differential by saying that now you can define a harmonic Beltrami differential on the upper half plane by replacing phi tilde phi mu with so you have to take multiply the quadratic differential with imaginary part of c whole square and then take the Schwarzian derivative or the quadratic differential and then take a complex conjugate.
How do you make the last one from A to S star from that?
Oh, so this is what I was keep on saying. So I said that all quasi-conformal transformation may or may not change the complex structure. So if the quasi-conformal transformation in the lower half plane for two Beltrami differentials are same, then that means mu and those two Beltrami differentials are equivalent, right? So that's why I am able to make this connection.
This many to one map, I want to get a sense of how many to one. So is it like discrete or other parameters? Is the number of parameters in the Beltrami differential the same as the number of parameters, continuous parameters, in the Beltrami differential, same as the number of continuous parameters in this quadratic form?
So there's something. So you are saying whether the null what is the dimensionality of the null vectors, right?
Is it some discrete kind of identification, or are you getting rid of a parameter? It sounds to me like you're saying that it's discrete because you said the number of parameters in the Beltrami differential was same as the number of parameters in complex structures.
Yeah.
And the number of parameters in phi is also the same as number of parameters in
Complex structures, yes.
So this many to one sounds like a discrete. Is this right?
Now the point is, when I look into the quasi-conformal map, it's true that Teichmuller space has a finite dimension, but at each point on the Teichmuller space you can find an infinite number of holomorphic maps, right? Analytic maps.
Yeah.
So those analytic maps are the one which corresponds to are the one which is responsible for making it many to one.
Analytic.
Yeah.
The space of the vector differential is a vector space spanned by the harmonic ones and the null ones. And if that is the picture, then it's clearly space of redundancy.
Redundancies, yeah.
Wait, so
I think the question is the null ones, how would it be?
But it is the vector space, not the space.
Sure, but
What is the dimensionality?
Yeah, that's what.
all the vector space we need to show that it's known.
wait, so right at the beginning I asked, how many modulo analytic equivalence classes, how was the number of parameters in the quasi-conformal transformation same as number
Exactly
of
same as.
complex
Yeah,
structures?
same as. Yeah. Modulo this analytic.
Right. Now these Beltrami differentials changed by the invariant under these analytic transformations?
So they are not, they are invariant.
They are.
Invariant, right.
Okay, so then the number of parameters in the Beltrami differential same as number of parameters in quasi-conformal
Yeah.
transformation. Modulo.
Modulo some small, exactly.
Modulo holomorphic transformation.
Yeah, yeah. So we already throw
Let's
out, right?
Let's
Yeah.
throw that out.
Throw that out.
So
Even with that, we have some modulo piece that we have to throw away.
Yeah, but I want, but number of continuous is the number of continuous parameters in quasi-conformal transformations same as number of continuous
Yeah.
parameters in complex structures?
Yeah, that is the same.
So is the number of continuous parameters in the Beltrami differential
Yes.
same as number of?
Yeah,
It,
it is same.
it is same.
It is same. So we have to
Then
remove a small piece, which won't really
which is
change that.
discrete, then?
Yeah, which is discrete, I think. Yeah.
Okay.
It's like it's removing zero modes. So you see the relation between phi and how we found a match mapping between the Beltrami differentials and the quadratic differentials. So we used an inner product.
Okay. Logic analysis, get one clarification. So, you said that there is an ambiguity in defining the WMUs, right? The analytic transformation.
In the lower half plane, there is no ambiguity.
No. Let's say let's start the upper half plane.
Okay.
So you can make an analytic transformation.
Yeah.
Right?
Yeah.
Of the WMUs. So that's ambiguous. Now you look at the description of that on the real line.
Yeah.
So
Yeah.
that presumably is also ambiguous.
Yeah. No. So
Right?
okay. Then.
I would think that if there is an ambiguity in WMU
Yeah.
to analytic transformation,
Yeah.
that will also affect its value on the
No.
real line, right?
No. So when I say that when you have some values are equal at the on the real line, so that there you are actually throwing away all the ambiguities, right?
So how?
So
let's not worry about the lower half plane right now.
yeah.
Just on the upper half plane.
Yeah. Yeah.
So in the upper half plane,
Yeah.
the WMUs are ambiguous up to the analytic transformation.
Yeah. That is true. Yeah.
So then on the real line also it will be ambiguous up to the analytic transformation, right?
No. So if on the upper half plane some things are related by analytic transformation, on the lower half plane they are exactly equal. That's why
So, for example, lower half plane, I'm saying on the real axis.
maybe up to some Mobius transformation. Some diffuse, right?
Yeah, so up to some difference.
Yeah, that is
So
true.
the
That I
WMU
agree.
is ambiguous, right?
Yeah. But
And
but the
now my understanding is the lower half plane you are getting,
Yeah.
that's the analytic configuration of that function. Right?
yeah, but the Schwarzian derivative will throw away all those ambiguities, right? A Schwarzian derivative of Mobius transformation or automorphism of full Riemann sphere is zero, right? So Schwarzian derivative will
Okay.
throw away all those analytic ambiguities.
I see. So you are saying somehow the ambiguity is totally up to this Mobius transformation.
Yeah, for
The
the
ambiguity determining WMU.
yeah, that is true.
Can you see the differential equation that WMU satisfies?
Yeah, W mu is equal to
So here we should be able to see the ambiguity.
yeah. So if you see if I so here if I make omega mu, if I find some omega tilde mu, which is a holomorphic function or something, see, so you have omega mu f of c, right? So where f is holomorphic, then you can see that there is some this holomorphic transformation is going to make some small ambiguity, right?
So it will not change mu, but
The solutions,
omega tilde is
yeah,
is
because the
satisfied.
left, yeah, that is true, yeah. So the left side you have no ambiguities because of this transformation, because anyway you are taking anti-holomorphic derivative, right?
And the number of these analytic quasi-conformal transformations that obey our boundary conditions, is that labeled by discrete parameters?
Yeah, so that's why we can identify this with the Teichmüller space.
But discrete, no continuous parameters.
No, so actually I'm getting a bit confused with the.
So nice, sorry. But your quasi-conformal transformations needed to satisfy this periodicity.
Yeah,
Quasi-conformal transformations could do it
Yeah,
because you do it easily because they had some knowledge. They didn't need to be analytic.
that is true. That is
However, the completely analytic
yeah,
transformations
Yeah,
that
these-
satisfy this periodicity property
Yeah.
are presumably very tightly constrained.
yeah, that is true because these are Mobius transformations,
up to,
right?
up to discrete parameters.
Yeah, discrete parameters, right, right.
Okay, what you're saying is the ambiguity between
That-
the Brownian differential and the quadratic form is these discrete parameters.
Yeah, which is thrown away by this.
From Mobius transformations, it's really not like that.
I thought it was like SL2,
Yeah, SL2. Yeah,
but preserving this gamma.
yeah.
You have to preserve
This particular that is true.
It's a discrete subgroup.
Yeah,
some discrete stuff.
yeah, that is true. So I think what Shiraz is saying is true. Like, so that ambiguity is what we are throwing away after taking a Schwarzian derivative.
Is that somehow the mapping class should tell
Yeah,
you?
I think so.
Yeah, yeah. No, I think so. Because anyway, I'm not mapping it to modular space. It's just mapping to Teichmuller space. So far I haven't touched mapping class groups. Yeah, for on the full complex plane. Yeah. On the yeah, yeah, on the upper. Yeah, yeah, yeah. So anyway, all those ambiguities will be thrown away for the quadratic differential. That's why we are able to find a map between the space of quadratic differential to the Teichmuller space, and then we can go back and see how we can pair a quadratic differential to a Beltrami differential. You can define an inner product between quadratic differentials and Beltrami differentials by saying that you are supposed to just integrate your object over the fundamental domain that corresponds to the Riemann surface, and then you just multiply phi c mu c and then integrate over all fundamental domains. So this provides you a pairing between phi and the quadratic differentials and the Beltrami differentials. So there could be a situation where you have a null Beltrami differential when if you integrate this with integrate the null Beltrami differential with the quadratic differential, you may end up getting 0. So this is like gauge transformation. So that's why we have some null direction in the space of Beltrami differential, but you don't analytic on the complex plane. Huh? It's a fundamental domain for the Fuchsian group or the Riemann surface, I should say.
You just say that all the null directions are removed.
Yeah. Huh?
You just said that all the continuous transformations are removed, right?
Yeah. Here I am just saying that see the mu that I am trying to pair with the phi's through an inner product is a random mu. It's not a harmonic Beltrami differential. It's a general Beltrami differential. So I'm just saying that. So this pairing is not one-to-one. There are still null directions. Now that's why I should do a filtering, so that Beltrami differential, if I take an inner product with a quadratic differential, should never produce 0.
No, but this is something I'm not understanding. I thought we'd agreed that the ambiguity in the Beltrami differential was discrete.
Yeah.
If so, there are no null. It's not like.
So I think these are just more.
Okay, so let's try to. I mean, let's.
So maybe.
go back to that.
Yeah, that's true. So you have. So what I am trying to make. Maybe then you can now say. So I have a space of Beltrami differential BH gamma. I am just saying that I can split the space into two.
So this is like splitting in the sense of a linear vector.
Yeah, yeah.
So this is I thought what we agreed was not fixed. I thought you told us that the ambiguities in Beltrami differentials were some discrete facts, none of the form of linear.
So what? I mean, you
So
can.
I misunderstood, but this is what I thought.
So what? I think one can try to count it, so whether that's continuous or discrete, by just saying that. So the same condition that you are saying. So you want a Beltrami differential, and then you could try to change the Beltrami differential through some Mobius transformations.
Some analytic transformation.
So analytic transformation that keeps the periodicity. Yeah.
Now, is that the space of those
Yeah.
Is the space of those discrete or continuous? I mean, this is an elementary question for, and I don't know the answer to, but I mean, I should, but. So for instance, suppose, yeah, what's confusing me is that the only two examples of Riemann circles that I know of, Nikhil sphere and
Yeah.
Torus, he's thrown out as
No, actually, I'm playing with a sphere here, right? This is actually a sphere, right?
Okay, then,
I think it's
yeah.
this ambiguity he's talking about.
What is this?
Nu tilde and nu tilde are the
Yeah.
lower half plane.
Yeah.
For that to happen, that f of z can be anything that's analytic in the lower half plane. And 0 in the upper one.
Upper.
It need not respect the visual distance on the term. So all we are considering is the periodicity when z belongs to upper half plane.
Yeah.
But there's one question.
No, even in the lower half plane, we need the
Is number of
periodicity.
continuous parameters in the Beltrami differential same as the number of continuous parameters in complex differential? I mean, there's a yes or no
I mean,
answer.
what I can definitely say that this space, the space of harmonic Beltrami differential, has exactly same dimensionality of the complex structure.
Okay,
And
you're saying
so I should admit that I don't know what's the dimensionality of n gamma.
But you're saying it could be greater.
It could be greater, or I don't have any specific comment. I know it for sure that this is the space which has to be matched with Taylor
What
space.
about the space?
I mean, it's just this condition that on the lower half plane there are two Beltrami differentials giving the same omega,
Yeah,
and that's what you want to get rid of.
yeah,
Now we have forgotten about the gamma
yeah,
condition.
yeah,
Just whether there are multiple Beltrami differentials that are giving the same omega.
yeah.
Then there is more ambiguity.
So one should,
Space of points that coincide in the lower plane, that do not.
yeah. So maybe I think the point is that when I compute,
Equation is definite. I mean, it's a only set, sequence equation.
yeah,
You're telling me the equation because you give me zero, and you tell me that at least the boundary, and then you have this equation.
yeah.
So, wait, could I ask you, is the number of parameters in the quasi-conformal transformation, number of continuous parameters, same as number of, let's respect gamma, same as number of parameters of complex structure?
So I mean, I don't want to make I don't know. Yeah. What I know for sure is that this is a space whose dimensionality matches with the Take-Muller space. Because anyway, I don't want to care about this space, right?
Okay, but how does it come about that?
So this is what I'm saying. So you have this pairing between Beltrami differentials and the quadratic differentials. I know for sure that quadratic differential is exactly same as the Take-Muller space. Now, through this pairing, when can you use a pairing through inner product? If the inner product doesn't vanish, right? So I'm saying that there could be Beltrami differential whose inner product between with the quadratic differential may vanish.
This integral is in the lower half plane?
Is on the fundamental domain on the lower half plane, say.
The lower half.
Yeah. Oh, yeah.
Mu is 0 then, right? Mu is 0 on the lower half.
No, so it's on the Riemann surface that I'm supposed to do this integration, right?
The upper half.
Yeah. I mean, I think I should just look into the precise definition.
You found the basis in the zero space.
Yeah. I think this is precisely what is done in Polchinski also.
So as a tensor, that differential there is what? It's 2 comma 0.
This one, yeah, yeah, 2 comma 0.
Okay, and that thing is -1 comma
Yeah,
-1.
yeah, 1.
So it's -1 comma 1.
Yeah,
So the whole thing is a 1 comma 1 form, and so
yeah.
we
Give me an area. Yeah.
Okay.
So that integral may vanish for some value, some Beltrami differential. I just want to throw away that. I don't even know what exactly is that space. Anyway, I don't want to even care about that.
Now -1 is the same as the dimension. Is this like the inner product between
B and
B and C?
yeah,
Like
yeah,
that?
yeah. It's exactly that.
Right.
So that's why I'm just saying this is what Polchinski does. So he takes the Beltrami differentials and multiply with the quadratic differential, and then count the throw away some of the null directions.
The null directions, are they always expected to respect gamma?
Yeah, that is. because even the null vectors are supposed to be defined on the Riemann surface, right? No, not harmonic property. They should have this periodicity property, because at the end you want this everything should be on the Riemann surface, right? So if you are demanding that everything is on the Riemann surface, that means they should satisfy periodicity. Doesn't matter whether that's a null Beltrami or something which can deform the complex structure.
Okay, so we know that if you have B del bar C,
Yeah.
okay, then are you saying that are you saying that the number of the ambiguities is the 1 to 1 corresponding to the C0 modes? Is that statement answer?
Yeah. So actually, that's why we are replacing the. Taking a pair between B and mu fields, right? Or the Beltrami differential. That's how we define the form itself.
Thanks. Okay, thank you. Simplified, okay, thank you.
Yeah. So yeah. So you have some. Yeah. That is true. Exactly. So that's why so these are the non-trivial solution belongs to that. That sector. Okay. So so the point is that once you can actually do the calculations and then compute the quasi-conformal map in the lower half plane, and then take a Schwarzian derivative to produce a quadratic differential, then you can inverse that relation, or corresponding to each quadratic differential you can define a Beltrami differential, and that Beltrami differential is something which always deforms the complex structure. So in that way you are finding an identification between harmonic Beltrami differentials and the Teichmuller space.
So if you take this mu of phi,
Yeah.
and then put it through this, then you should end back with phi mu.
Yeah, phi mu. So in that situation, so you see that if I replace mu phi, if I take an inner product between phi and mu phi, it's always less than 0, because you have so you have a mode of phi square sitting there with minus.
There maybe you can see ambiguity.
No, so with this one you won't see any further ambiguity, because it's
Then you'll probably be able to see what extra things we add to it.
so see. So if you have an inner product with yeah, so this yeah. So what I gained is that I constructed the space of Teichmuller the Teichmuller space using harmonic Beltrami differential. Now I will show you why I am interested in this. So let me consider a path in the space of harmonic Beltrami differential. So I have a path inside. I want the Beltrami differentials, or the harmonic Beltrami differentials on this space should vary along this curve with respect to a parameter t. So now what I can do is I can take a derivative with respect to t and then identify this with the tangent vector, right? So that's in that way I am at the end finding what are the tangent vectors on the Teichmuller space. And that's the reason why I went through all this machinery. Now I will show you that I can actually use it to compute something explicit.
So mu was your canonical Beltrami differential.
No, this one is harmonic Beltrami differential. So I am just supposed to let them vary through a particular curve and then take derivative to find what are the tangent vectors. So I could find enough number of curves which will form a basis for the tangent space of the Teichmuller space, and then construct all the tangent vectors. Once I have tangent vectors in the Teichmuller space, I can take an inner product between the B fields and then use this them to use such an inner product to construct a differential form in the Teichmuller space. That's what the form that you are supposed to define in to compute the string amplitude. So let me define.
Can I ask this one question?
Yeah.
So this harmonic differential essentially maps to the space of quadratic form.
Yeah. Yeah.
Then
Define on the lower half plane.
right. On the Riemann surface.
Yeah. Image of the Riemann surface. Right.
Then there are more elementary arguments which shows that the complex structure, because the final two statements are purely complex.
Yeah.
Right, there is no non-image scale there.
Yeah.
In the conclusion.
Yeah.
Is there a completely analytic path to that answer?
I don't know anything.
In other words, if this holds another dimension.
Oh, you mean okay. That I don't know.
It's dependent on.
So actually, to even compare, I don't know anything about higher dimensional situations. Maybe there is. I don't even know, because I never studied the situation where I mean I never studied three manifolds or four manifolds.
Do you know what the cases are?
So yeah. So now I think we have enough material background to define the top form on the moduli space or the Teichmuller space. So to define a top form, first we have to introduce this B field and C field with the usual action. These are the ghost fields with usual ghost action. Then B and C are anti-commuting bosons. So you can use them to define a differential form. So the way we are doing is the following. So we should first observe that the B field transform like a quadratic differential. And you have a Beltrami set of Beltrami differentials or harmonic Beltrami differentials. So and we also know that the dimensionality of the space of harmonic Beltrami differential is 6h minus 6 plus 2n for a genus H surface with n number of boundaries or punctures. So we can find this many number of basis harmonic Beltrami differentials. So you could think that a random Beltrami differential, a harmonic Beltrami differential, can be expanded as expanded at a particular point in the Teichmuller space. I am assuming that M1 to M6h minus 6 plus 2n provides me a coordinate for the Teichmuller space. And then I can choose a particular point in the Teichmuller space, and then I assume that with respect to around that point, I can choose a neighborhood, then find the tangent space or define the tangent space at this neighborhood or at this point. So I can expand any harmonic Beltrami differential that belongs to this neighborhood around this point as follows. So you have a leading term plus delta mi. There is a variation of the parameter, the Teichmuller space coordinates, and then I assume that there is a coefficient which is again a Beltrami differential, which depends on the base point. And I runs from 1 to 6h minus 6 plus 2n. So that means the basis vectors. By this I just mean to say that the basis vector for the harmonic Beltrami differential at a point or the tangent space of harmonic Beltrami differentials are given by phi v phi I, where I runs from 1 to 6h minus 3 minus 6 plus 2n. Now I can take this many number of B fields and take an inner product between all these basis Beltrami differentials, and this will provide me the top form on the Teichmuller space. So let's say I have n external state with some quantum numbers a1 to an. Then this is given by the path integral dx mu dc dv dc bar. Vj, this is an inner product between Vj and B field, and then plus you have an inner product between the conjugate of Vj bar and B bar. And yeah, so this is the zero mode part, and this is the part which is providing you the differential form. You see that you are multiplying the tangent vector with the anti-commuting object.
Plus, but plus you mean sign.
Oh, it's just plus. So see, I'm just multiplying with 6 h minus 6. I'm not assuming that the parameterization of Teichmuller space is analytic.
So you have to have as many B insertions and as many B bar insertions.
Yeah.
Number of objects.
Yeah. So you know the top. See, you can think of this each term as some differential.
Oh, and
Right.
then product. Is
Then
also
product.
next.
Yes. And then you are supposed to take the top form out of it, right. So. So and usually we don't have to do this plus sign because we are already assumes that the parameterization of the Teichmuller space is complex. And I'm not going to use a complex parameterization of the Teichmuller space. In fact, there is no such complex parameterization of the Teichmuller space which is convenient for doing any calculations, except the period matrix case. So that means if I compute, if I am able to come up with a nice parameterization of the Teichmuller space and then compute the associated basis harmonic Beltrami differential, I can explicitly write down this top form. Then take this top form, integrate the top form over the whole moduli space MHN to obtain the string amplitude. So here I am supposed to multiply with the all the vertex operators. Each here. Oh, x mu. Yeah. So x mu won't participate in making a differential form. They will be there in the vertex operator and in the action part. So it's a Gauss field that is the one which we are using to produce the differential. Yeah. So here the only unknown thing is that first of all we have to choose a particular parameterization of the moduli space, then find out what is the basis Beltrami differential that spans the tangent space at a point in the moduli space. So now I will choose a specific parameterization of the moduli space. So before that, let me tell you. So this is the answer for the closed bosonic string theory. If I want to write a similar answer for superstring theory, I am supposed to insert enough number of picture changing operators. So we have two problems to solve before evaluating a superstring amplitude.
Sorry, I should notice that if I change, you've not said anything about the normalizations of these new values.
About the
normalizations of your basis Beltrami differential.
So this is the one which this quasi-conformal this is the Beltrami differential that produces a variation in the parameter by delta mi. So in that sense, there is nothing more. There is no.
And then you're integrating over the space.
Yeah.
So that you connect the two.
Yeah. So this is exactly this piece
So
I am.
the change in base.
Yeah, that is true. So this is the object that I am inserting here. So there is no ambiguity about the normalization. So that's why I was saying when you compute a differential form in the moduli space using string theory principle, there is nothing you are supposed to do for finding the normalization. There is no ambiguity in normalization. You give the full root, and this object will factorize without even adding any extra factors. So this is the answer for closed bosonic string theory. Now if I want to go ahead and then write down a sensible expression for superstring amplitude, I have to do a little more work. We know that in superstring theory we have to insert some number of picture changing operators to take into account for the fact that the world sheet of superstring theories are actually super Riemann surfaces, not the usual Riemann surface. Somehow we can forget about the super part by inserting enough number of picture changing operators. So these are some operators that you are supposed to insert on a world sheet. So we can choose some specific distribution of PCOs depending on how many number of picture changing operators are needed on that particular surface. Now the condition that this distribution has to satisfy is that if I perform a mapping class group transformation of the Riemann surface, the distribution of picture changing operators should not change. Since I am inserting, so see the vertex operators are inserted at the punctures. MCG will not act on the puncture. MCG will keep the puncture untouched. But any point on the Riemann surface other than puncture will be transformed under the action of mapping class group transformation. So you have to find a appropriate distribution of PCOs on the world sheet so that under a mapping class group transformation you won't change the PCO distribution.
What do you mean PCO distribution?
So you see you on a genus or on a world sheet with H handles and N punctures, say I have NS punctures, I am supposed to insert 2H minus 2 plus NS number of picture changing operators. So I could choose a specific gauge so that I am supposed to, I can insert picture changing operators at 2H minus 2 plus NS number of locations. So I should find a appropriate way of distributing this many number of picture changing operators such that under the action of MCG,
Distributing between where and where?
on the surface I can say I can insert the first PCO at some point, chi1, and second PCO at some other point, third is chi3, chi4, chi5. So if I do a mapping class group transformation, these points may go somewhere else. Now at the end I get a distribution. So I have to match with the initial distribution and this distribution and see whether the distributions are changing or not. Or the object related to PCO distribution should not change under any diffuse.
Sorry, at least naively the amplitude doesn't depend on the location of the picture changing operator.
No, the point is that depending on the location, so you are talking in terms of precise location on the Riemann surface.
Yeah.
You are saying that all those locations are in that statement you think that locations on the Riemann surface, since Riemann surface is invariant under MCG transformation as an abstract object, a location also should not change, right?
I think you're just saying the amplitude should not depend on where the
No, that's what I'm trying to state.
just from physical.
Yeah, just from physical statement. So you are visualizing this particular Riemann surface, but as a Riemann surface, I could change the shape of this object. Then you have to check the mathematical structure, whether the mathematical structure, which is a complex structure on the deformed shape of Riemann surface and this Riemann surface is same or not, right? When you say a Riemann surface, you are assuming that these two are exactly equal.
Yeah,
I think the way one can think of it this way, that let's suppose that you have a one puncture torus and you specify the PCO location as a function of tau. Okay, tau is a modular parameter.
yeah.
And now suppose you go from tau at one boundary to the other boundary and the tau goes to tau plus 1.
Okay.
The PCO has to move so that it comes back to the original point by the time you have gone to 1. So suppose you have gone from the left boundary to the right boundary, right? Other tau goes to tau plus 1.
Yeah.
You have to specify the continuous line that the PCO follows as you are moving this, as you are moving in tau.
I understand. You're saying otherwise you haven't specified where the PCOs are in an invariant way.
Exactly. Yeah.
Yeah.
Then
That is the discontinuity, right?
yeah.
I mean, then it's like tau equal to 1 minus epsilon and tau equal to 1, you have a discontinuity.
Yeah. Yeah. But would you care since it does, at least naively it doesn't matter where the PCOs are?
No, I mean,
from the abnormal, the PCO locations vary continuously. And you choose a major. You don't care. But here you are having a discontinuity, right?
Okay.
So let's imagine that you choose a PCO location. I mean, so what happens when you say that the amplitude doesn't depend, the integrand depends on it, and you change by total derivative,
yeah.
right?
Oh, I see.
So
Yes,
you are
I get it.
integrating total derivative.
Total
And
derivative
if
on
there is
moduli
some-
space. And
Exactly, yeah.
Okay, and then if there's a discontinuity, you get a surface there.
Yeah.
Yeah.
So what you think of as a closed curve in the moduli space,
Right.
I mean, you see somewhere in the closed curve, the PCO location has jumped, right? Because you have not chosen the correct periodicity.
I see. Thank you.
So that, yeah.
So the reason is that when you actually study the Riemann surface, we are using a representative of Riemann surface. A representative of Riemann surface is not invariant under mapping class group transformation. And you are choosing a point on the representative of the Riemann surface. Under MCG, that will change. That's why I'm saying a PCO distribution in general may change under the MCG transformation. If you are not choosing a PCO distribution that is not MCG invariant, then there is a trouble. The trouble is that we are supposed to use this PCO distribution to define a differential form on the moduli space.
Yeah. So as I should clarify, the distribution means locations as a function of complex.
Complex structure, exactly.
Right.
Yeah.
And that should have the invariance.
That should have the invariance. Yeah,
Because everything should have the invariance.
exactly. Yeah. So we should be able to find such a PCO distribution. If you are not able to find such a PCO distribution, we won't be even able to define a superstring measure. This is one challenge. And second challenge is that if you want, I mean, this is just a formal expression. We want to find, at the end, we want to evaluate it, right? So to evaluate it, first of all,
But Roji, you could take averages, right?
yeah, that is true. So that's what I mean.
For key concepts here,
Yeah,
there is no particular point on the sphere which is invariant under arbitrary permutation of those three concepts, right?
that is true.
But you can take average of the 2 points.
Yeah,
Which will be invariant.
yeah. So when I said that I should find a PCO distribution that is invariant under MCG, I actually mean this averaging, so that I get an MCG invariant distribution, right?
But in general, instead of integrating over the diagonal space divided by mapping class group, can you not integrate over the diagonal space itself?
Actually, I mean, it's a highly non-trivial procedure. That's what I will describe. I mean, that's not a trivial procedure. If you are supposed to do a computation on the moduli space, you should do it on moduli space. You should not do it on Teichmüller space. If you are doing it on the Teichmüller space, then you should be able to find a one-to-one map of this computation to Teichmüller space.
But is it unphysical in
It's unphysical, right?
diagonal space is not model space?
Yeah, it's actually unphysical, right? So the moduli MCG, the size of mapping the moduli space is much less compared to the size of Teichmüller space, right? So you are overcounting everything. You are overcounting things infinite times. So you will get
But
divergences.
you are integrating over
So that's why it's actually a technical problem. So the second challenge is that you should first you should choose a nice parameterization for the Teichmüller space. Unfortunately, we don't have nice parameterization for the moduli space directly. In general, we have a nice continuous parameterization for the Teichmüller space. So choose a particular parameterization for the Teichmüller space, then find a fundamental domain inside the Teichmüller space that corresponds to the action of MCG. So just like the case of torus. So you have upper half plane, which is the Teichmüller space of torus. Now you know that what is MCG, and then use that to figure out what is the fundamental domain over which you are supposed to perform integrations. Right? So this is the case for torus. Now if I want to do it for higher genus surface, I should always start from I should start from the Teichmüller space and then first find out what is exactly the group of the mapping class group, then figure out what is the fundamental domain inside the Teichmüller space that corresponds to the mapping class group. Then I am supposed to perform computation only within a fundamental domain. If I forget that, I am just doing the calculation several times and then getting infinity. That which is not even physical. It's just a wrong calculation. So that's the second challenge. So you have to solve two problems. First, a problem of distributing picture changing operators in a MCG invariant fashion, and then finding a proper parameterization for Teichmüller space and then a fundamental domain inside it. So the parameterization that I will I choose is the Fenchel-Nielsen parameterization. Anyway, I don't have time to discuss the PCO distribution thing, but it can be done.
Of course, this is highly non-unique, right? This PCO distribution.
Yeah, it's highly non-unique.
Anything that comes back to it, there are many ways to come back to it.
Yeah, there are many ways. I can even I can provide you at least 2 ways, or even more ways. So so that requires knowing a lot about the action of MCG on a Riemann surface.
Right. I mean, it's just that. Yeah. Any part.
So I discussed everything to get into this point. So I'm going to use a parameterization of Teichmuller space, which is known as Fenchel-Nielsen parameterization. So the basic idea of this Fenchel-Nielsen construction is the following. So let's start with a hyperbolic Riemann surface, and then say you have h number of handles and n number of punctures. So the idea of Fenchel-Nielsen construction is the following. You can get any Riemann surface, hyperbolic Riemann surface with h number of handles and n number of punctures, or geodesic boundaries, by gluing 2h minus 2 plus n number of pair of fans, hyperbolic pair of fans. So we saw, I think in the second or first lecture, that the complex structure of a pair of fans, hyperbolic pair of fans, is uniquely fixed once you specify what is the boundary length. The length of boundary geodesics. Once you specify the length of boundary geodesics, then you are uniquely fixing the complex structure of a pair of fans. So you see that with some parameter, you are able to fix a complex structure of some component surfaces of a full Riemann surface. And then, see, you can start from genus H Riemann surface with n bordered, and then find 3h minus 3 plus n number of mutually disjoint simple closed geodesics such that once you cut the surface along these geodesics, in this case one possibility is of this kind. If you cut along this geodesics, you are actually producing 2h minus 2 plus n number of pair of fans, hyperbolic pair of fans. So that means you have 3h minus 3 plus n number of simple closed geodesics. Once you specify the length of this many number of geodesics, say L1 to L 3h minus 3 plus n number of lengths, you are actually fixing the complex structure of component pair of fans. Now you can take this component pair of fans and glue them, and before gluing you could do you could perform a twist. So you have a sphere with 4 holes, which can be obtained from 2 hyperbolic pair of fans. So you should first assume that the geodesic length of the boundary of the pair of fans P1 and the boundary of our interest of the pair of fans P2 must be equal. And then before gluing you could perform a twist, say tau, and then again you will get a hyperbolic Riemann surface. This is a non-trivial statement. Yeah, exactly. This is like a highly discontinuous way of changing the complex structure of Riemann surface. So you could look into a seam on the hyperbolic sphere with 4 holes, and then you are cutting along one simple closed geodesic, and then you are performing a twist such that this seam will go somewhere here. Now once you glue them back, then you get another surface where you have a seam coming from here and then going back in a discontinuous way and then coming here. So now you are this is not hyperbolic surface. So you have to pull the seam and tighten that by changing the metric on the surface. So that you end up getting another hyperbolic sphere with 4 holes with continuous seam. This is the idea of varying the complex structure on higher dimensional, higher genus surface by performing cutting and gluing after twisting.
That last transformation will be a continuous one?
This, which one?
Going from a discontinuous seam to in the middle?
Yeah, that's true. So it looks like highly a discontinuous transformation. So to begin with, this was studied by Fengel and Nielsen by just studying the Fuchsian group. So this kind of cutting and gluing can be understood purely using group theory. And then you could do algebras and show that you have this many number of parameters, L1 to L3h minus 3 plus 1 and tau 1 to tau plus tau 3h minus 3 plus 1 and number of real parameters. And these, when you vary these real parameters, the non-trivial statement by Fengel and Nielsen is that they somehow showed that they are producing all possible hyperbolic Riemann surface having s number of handles and n number of boundaries, which is a highly non-trivial statement. So, but the construction looked discontinuous. Then, what Wolpert has done is the following. Yeah. So the only thing which I know is that you could just map the homotopy to some of the generators of the Fuchsian group or the closed geodesics. Yeah, there should be. There should be some object inside the Fuchsian group that tells what is the number of. Yeah. So maybe I presume that you can look for the normal subgroups, cyclic groups inside the Fuchsian group, and then that will count you, and then see how many independent number of disjoint cyclic groups are there. So that should tell you how many handles are there, and then how many number of parabolic elements are there. That will tell you how many punctures are there, right?
Okay, Roji, maybe I'm asking the questions again because I didn't get the last question. So the point, if you look at the Fuchsian group,
Yeah.
these L's and tau's are some parameters labeling the generators, right?
Yeah.
So is it known what the correct relation is?
Exactly. Yeah.
Can I write down the generators in terms of L's and tau's?
Yeah. It's known. In
I see.
2010,
Then it is popular.
actually, if you are providing me a location inside the Teichmuller space parameterized by this Fengel-Nielsen coordinate, I can write down what exactly is the generator in terms of this L and tau.
I see. Okay.
So that there is a systematic algorithm for constructing that. So which happened only in 2010. So Moskit constructed that.
So for the 4 punctures here,
Yeah.
where all these 4
Yeah. Point.
the way we count the moduli is 3 or 4 2.
Yeah.
The fourth one, wherever it can make it.
Yeah.
So here it seems to depend on the chopping off of that.
See if it is a 4 punctured sphere, you have only one moduli parameter, right? And that's a complex parameter. That means you have 2 real parameters. Here you have only one, or you have only 2 real parameters, right? Which is length and twist. Oh, that's actually a difficult thing to answer. So the relation between the location of puncture and the Fengel-Nielsen coordinate is extremely hard to find.
Because a puncture in this way of looking at it corresponds to L equals to 0.
Yeah. So you have to solve this Fuchsian equation, which appears.
That is the max, right? Even though the external L goes to 0, there is internal L and internal rotation. That's complex number. So here, this puncture can be because of the
Yeah. Yeah.
So, okay, so in the pair of primes, we take 2 of S to 0.
Yeah.
We constant.
But the precise relation between them, I mean, it should be possible. So it's like solving this inverse uniformization problem, where you say that you have one kind of parameterization for the moduli space, and you have some another kind of parameterization for the moduli space. There should always be a relation connecting two different parameterizations. But I don't know of any situation where people know the relation between two kinds of parameterization. There is some problem which hasn't solved yet. Actu- So now my task is to show you that, I mean, I provided you a parameterization of Teichmuller space. Now I have to show how I am going to compute the harmonic Beltrami differential or the basis of harmonic Beltrami differentials that corresponds to this Teichmuller space, right? Only then I can construct a tangent inside the Teichmuller space and then construct a top form for the string theory amplitude. So that's why, so far we had so many abstract discussions and we found a formula which is mu phi, which is this is a formula for harmonic Beltrami differential. Mu phi equal to minus 2 imaginary part of C whole square, and then we have to compute the associated quadratic differential and then take the complex quantity, right? So here what we did was that, so you started from a quasi-conformal transformation and then use that to find a quadratic differential and then use that quadratic differential to find a harmonic differential, right? So we have to do this step. For that, first of all, we have to find what is the quasi-conformal version of Fengel-Nielsen twist. So here we said that I can cut along a simple closed geodesic on the hyperbolic surface, and then I choose a closed simple closed geodesic C, cut along this simple closed geodesic C, and then perform a twist, and then glue back. That will provide me a new surface, right? So assume that you have the surface R, and then you perform a.
Is there an analog of these coordinates for Riemann surfaces with punctures?
Yeah, actually, when you have the coordinates for Riemann surface with borders, you always have the coordinates for the Riemann surface punctures by saying that the boundary length should go to 0, right? So you have some boundaries for the Riemann surface. You can take them to 0. So that corresponds to Riemann surfaces with punctures.
Okay, if you use this tau I and
Li,
right?
yeah.
Then you don't have the coordinates for the punctures. I mean, you have to add them, right?
No, that already contains the coordinates for the punctures.
How? Because I thought you.
So see,
Okay.
yeah. So that's why it's very hard to really distinguish between what is the coordinate corresponding to puncture and what is the coordinate corresponds to the handle. Actually, that is the way we should do string theory. Otherwise, you won't be able to really deal with this IR divergences. That's why I feel Fengel-Nielsen parameterization is very well suited for doing calculations in string theory. I mean, there is no ambiguity. If I use puncture location, definitely I have to be very careful about my contours in the moduli space.
Okay.
So here, I can even write down a contour default. So the I epsilon prescription for string theory is extremely straightforward in this formalism. It's extremely straightforward. So the calculations will end up like quantum field theory calculations. So if once I use hyperbolic surfaces, string theory somehow is becoming more like quantum field theory. So that's why I feel this formulation is extremely suitable for formulating a string field theory. Yeah. Yeah.
But in the case of, let's say, spiralist poles,
Yeah.
it's real.
It's
Three real
No, actually, you have to fix the boundary length, right?
Yeah.
Once you fix it, then you don't have any moduli space.
Yeah, but another way of saying it is the model space is parameterized by the boundary length.
Yeah, if I want to just say that I have a sphere with boundaries without specifying the boundary length, then you are correct, right? So you have
Three real dimensions.
Yeah, you have 3 real dimensions. So you can use the Euler characteristic formula.
You have punctures and without poles, it's complex.
Yeah. So when you have punctures, you don't have analytic structure. When you have holes, you don't have analytic structure. Only when you have punctures, you have analytic structure for the Teichmuller space.
So it is like an open string mix
holomorphic energy response.
Exactly. Yeah. So my next task is to tell you or explain you the quasi-conformal version of Fengel-Nielsen twist. Only then I will be able to find a nice tangent vector on the Teichmuller space, and then once I find a tangent vector corresponding to each vector field del by del tau I and del by del Li, I will be able to write down a differential form in the moduli space. So for that, let me explain what is a quasi-conformal map that corresponds to a Fengel-Nielsen twist.
Tau is the angle.
Huh?
Tau is the angle.
Tau is the twist, right? Angle, exactly. So let me look into a closed geodesy on a Riemann surface R, and then I am going to cut the surface along C and then twist it by a small parameter T, and then I obtain a new Riemann surface which I denote by RT. So what I can do is, what I am doing can be thought in a two ways. Right? So you see that there are seams or geodesics passing through the closed geodesic C, right? So you can look into the perpendicular rays that is passing through the closed geodesic C, a set of rays, and then you perform a twist. So the Fengel-Nielsen twist does the following. So it fixes the left side and then rotates the right side, so that the rays in the right side will not match with the rays in the left side, which was matching in the previous situation. So this is a Fengel-Nielsen deformation. Now I am going to tell you a quasi-conformal deformation. For that, around the geodesic C, let me choose a small annulus, so which has some width WC. So WC is a collar with around the geodesic C that has length or that has a distance from the closed geodesic C, hyperbolic distance, less than some value A. A is the width of this collar. Now there exists a theorem which is known as Collar theorem that says that if, say, the length of the closed geodesic C is LC, then if the width of the collar that I am considering is less than say less than or equal to sin h inverse of let me just look at it. 1 by sin h LC by 2. If the width A satisfies this condition, then I can think of WC as a part of hyperbolic annulus. So when I look into collars that has length very small, then I can see that I am getting a hyperbolic annulus around the curve which has a long length. Right? So you are actually producing long propagators when you are degenerating it. When you are surface which is far away from degeneration, you say that you have a length for the closed curve much greater than some particular value. In that situation, you are actually shrinking the width of the hyperbolic annulus. So we have to assume that the collar that we are considering has very small width.
The collar, I thought you just glued and the collar was in your head.
Yeah.
Now you can see. I didn't understand.
So I haven't said why I am using this theorem, right? I just said that I am going to choose a collar around the closed geodesic C that has length very small.
Yeah, and sorry, and if it has length very small, then what good thing happens again?
Yeah. So the thing is that then I can map this region to the upper half plane. This particular collar, so there is an image for this collar in the upper half plane which looks like a small annulus which you chop by two rays. So you get a section of an annulus on the.
That inequality ensures what? Please again.
So this inequality ensures that WC has the same metric as that of a hyperbolic annulus, and hyperbolic annulus is generated by one single generator.
Hyperbolic annulus. But did you tell us that all gluing had this property?
Yeah. There is another theorem which says that if I have two mutually disjoint closed curve on a hyperbolic surface, I will always be able to find two independent neighborhoods which can be thought of as scalar. And that is the reason why this Fenchel-Nielsen twist business is working. So I can do deformation locally. Unlike the situation where you use this idea of I forgot that. Ashok, do you remember the name of that construction that you use for constructing the tangent vectors? Yeah, Schiffer variation. Yeah. So Schiffer variation is something which is not a local variation. So you do a variation for the local coordinates around every punctures on the surface. You don't really worry about the interior. You can actually do a Schiffer variation in the interior also, but the Fenchel-Nielsen twist is actually very difficult to think in terms of Schiffer variation, because this is a highly localized transformations that you are performing. So that's why I have to always look. I can always look into a region, a small region around a closed geodesic with respect to which I am doing this Fenchel-Nielsen twist.
The point is, the Schiffer variation is also local, right? I mean, you are doing this twist, matching on every boundary of every disk, right?
That's true, yeah.
So in that sense, that's also local.
So maybe one can think that this is a very special case of Schiffer variation. Maybe in that sense, yeah. But definitely you can't vary it.
Variation has a specific, this thing that you vary around the disk around each function.
Yeah,
Right?
yeah,
Whereas here you are varying it in the interior, the reverse surface.
yeah.
You are just using two different cards where you are doing the math, where you are doing card.
That is true. So, but if I choose variations of this kind, then I mean it's actually useful at the end.
For degeneration, yes.
For degeneration.
Schiffer variation is not good for describing degeneration.
Degenerations, yeah, yeah.
This is probably good for describing degeneration.
Yeah, that's why this whole parameterization is extremely similar to quantum field theory. So in quantum field theory, degenerations are, you are actually in the degeneration, right?
So here degenerations will be when one of the glued L's goes to 0.
Exactly, yeah,
Right.
yeah. So you see the situation is more or less like string is becoming a point particle. So the picture is very neat from the point of view of field theory interpretation. So maybe this might be extremely useful for getting field theory corrections, string theory correction to the field theory amplitude. So anyway, what I do is I just take a small collar around a closed geodesic, and then what I do is the following. I don't do a discontinuous transformation. I take these rays and then don't touch these rays which is outside this collar, and then inside the collar I start varying the rays in a small way, so that the whole variation is happening inside the collar, and at the end it matches with the rays which is in the outside of this collar. So you have left side you had set of collars, and on the left pair of fans you had set of collars, on the right pair of fans you had some another set of collars, rays, right? Yeah. So it's more like regulating. So you are actually regulating this discontinuous transformation by a continuous variation. So you are changing the complex structure very slowly. So you have set of complex coordinate here, and then Fenchel-Nielsen twist is saying that, see, you cut along some particular closed geodesic, and then say that on the right side you have new complex coordinate, which you obtain by multiplying with a shift factor. So here what I am doing is that I am not doing that drastic change. I do it in a continuous fashion. Yeah, on the upper half plane, see, I assume that WC has appropriate width, so that I can think of this as a hyperbolic annulus, and the image of a hyperbolic annulus on the upper half plane is just like an annulus. So this corresponds to a hyperbolic annulus that has infinite length. Now I want to chop off some region so that the width matches with the width of the collar on the surface. So that means I can always find an appropriate value, an angle theta 0 between the imaginary axis and the rays that I am using to chop the annulus, which I denote by theta 0. Exactly, yeah. So that's why it's measure has this nice separation, degeneration behavior. So this is my region of interest. So inside this, on the upper half plane, you can see that, see, initially you had a, here what I assumed is that the closed curve is represented by scaling C going to lambda C on the upper half plane. This is the particular element of Fuchsian group that I choose to match with the closed geodesic. So this is one assumption. So the element gamma C that generates the closed geodesic C has fixed points at 0 and infinity. So that the fundamental domain of the this scaling transformation looks like this. So here I assume that the point of intersection for this annulus on the imaginary piece here is I, and here I have I lambda. Now I am supposed to identify I and I lambda, so that my cylinder is coming from by folding this side, and here I have width. So this one a long ray along, which cuts the closed geodesic on the Riemann surface looks like a arc on the upper half plane. So it is this arc. This is the ray with which I start. Now, when I do the Fenchel-Nielsen quasi-conformal deformation, I am supposed to vary it in a small way. So here I have some ray, and the ray will be changed to something else inside the collar, and outside from here onwards is just another geodesic. So here I had a geodesic which I actually deform inside the collar region. So the good thing is that now I am able to see a continuous variation on the upper half plane. Now I can write down what is a precise quasi-conformal transformation that is generating this kind of a variation for a ray. So which is a simple one. So the quasi-conformal transformation that I am supposed to perform on the upper half plane has the following form. So we have a conformal transformation which induces this twist by amount t on the upper half plane looks like this. So, so C is the coordinate on the upper half plane. So you have C untest for all those values of argument of C that lies in between 0 and pi by 2 minus theta 0. So that just means that in this side I am not touching the rays, and then once I enter into the collar, I am slowly varying the phase factor, so that the coordinate varies becomes C into e raised to minus t by 2 theta 0 argument of C minus pi by 2 plus theta 0 inside the collar is given by pi minus 2 minus theta 0. And then once I pass the collar region, I am supposed to stop my deformation, so that it becomes c into e raised to minus t for pi by 2. So here we constructed an image of quasi-conformal transformation on the upper half plane. So see, this deformation is not invariant under the full transformation generated by an arbitrary element inside the Fuchsian group. So this this quasi-conformal transformation does not have the nice periodicity properties. So once you compute the Beltrami differential for this quasi-conformal transformation, you will get a Beltrami differential, but that Beltrami differential has the periodicity property only with respect to this generator gamma 0. So I can easily compute that by using the fact that argument of c means minus I log of c by c bar. So one can easily compute the Beltrami differential, and then we obtain see, so I am just using a fact that I am looking into a particular region, right? I don't care about the global part. Now that's something which I can't do. At the end, I have to make sure that if I am doing something on the Riemann surface, whatever the symmetry transformation that I do on the Riemann surface should not change the differential, right? It should only give a fact. Yeah.
As being obtained by quotient in the upper half plane
Yeah.
something.
Yeah.
Then this patch
Yeah.
will have images various places.
Yeah.
Which will become that.
So the point is that this is
and this process is going on against that, right?
no, that is true. But when I look into the full fundamental domain, this somehow fits into, but it's not exact fit, right? It's an approximation. So you are only worrying about one periodicity. So this ray could have gone to some other part and then come back through the some other non-trivial cycle, and then again come back, right? So those kind of symmetries I am somehow forgetting. So that I should not do. So that's why I am saying whatever quasi-conformal transformation that I constructed is not precisely the quasi-conformal transformation that I want for the Riemann surface, but I can always make it by taking the images. So the mu t or the tau t is the Beltrami differential for this twist on the upper half plane is given by minus I t for theta 0 I theta c by c bar on any point on the upper half plane. So here I assume that chi I theta is some function that is 1 only when theta is between pi by 2 plus theta 0, pi by 2 minus theta 0. So that Beltrami differential has support only inside the collar. So now you can use the idea of method of images and then construct the full Beltrami differential. Once you constructed the Beltrami differential, we are going to repeat whatever we discussed in the starting. So we obtained, so after taking the Poincare sum, so you can easily see that this object is invariant under the transformation C going to lambda C. Since lambda is a real parameter and lambda is equal to e raised to L of the e raised to minus length of the closed geodesy. So the differential that I constructed transform in a nice way only for the element that generates the closed geodesy. So I have to make it into a Beltrami differential on the full surface by taking a Poincare sum. So which is just or the method of images. And it's given by tau of gamma c and then multiplied with d gamma dc bar divided by d gamma c DC. And we are supposed to sum over only those elements inside the Fuchsian group which you obtain after moding out with the cyclic group gamma 0. So this is a Beltrami differential that generates the Fenchel-Nielsen twist. So we constructed that. Now we can take this Beltrami differential and then extend it to the full complex plane. So you could write a new Beltrami differential mu tilde C by stating that on the upper half plane it has non-zero value and the lower half plane you have 0. Now one can compute the for small values of t, you can construct the quasi-conformal transformation on the full complex plane, and I can write down the answer. So by just solving it, so the answer looks like this. So the quasi-conformal transformation f mu tilde T C is given by C plus T f dot nu. I will explain this, nu C plus product T square. So here the second term is just the derivative of df dt. So if I can find the form of second term, that means I am actually solving the Beltrami equation for this particular choice of Beltrami differential. So the solution is known, and the solution takes the following form. So here I assume that mu t can be expanded as t into nu c plus order t square. So with so this is the nu that appears here, and f dot nu c is given by 1 by pi and integral over the full upper half plane nu theta c into c minus 1 divided by theta minus 1 theta minus c d theta where, and the theta belongs to h and c belongs to lower half plane. So what I am getting is that somehow using the so-called Cauchy-Pompo formula, which is just the generalization of usual Cauchy formula, one can solve this the Beltrami differential equation having this particular choice of Beltrami differential, and write down what is the quasi-conformal map. Then you can, so this is a quasi-conformal map that we constructed on the lower half plane. So I constructed the quasi-conformal transformation on the lower half plane, which I can use to compute the quadratic differential on the lower half plane. And then I can use that quadratic differential to compute the harmonic Beltrami differential on the upper half plane. And that's given by mu phi t c given by I into t divided by phi imaginary piece of c whole square with some phi c complex conjugate, and phi c is given by I 2 pi 1 by gamma c d gamma c divided by dc whole square, and gamma belongs to all elements in full Fuchsian group mod out by cyclic group. So what we obtained is, we obtained what an infinitesimal solution for Beltrami, harmonic Beltrami differential, which can be used to compute the tangent vectors. So what we are gaining is we are computing the tangent vector for the twist transformation that we performed with respect to a closed geodesic C, and that's mapped to the Beltran-Mill differential d by dt mu t phi evaluated at t equal to 0 as given by minus I phi and the same object. And we know explicitly what is that object. It's a sum over Fuchsian group. So after doing all this abstract thing, we are able to precisely, we are able to get an explicit form for the tangent vector. That corresponds to the vector field del by del tau. So now I haven't constructed the tangent vector for the length vector field.
Okay. Can I just ask one thing, Yogi?
Yeah.
Yeah. I mean, instead of constructing a tangent vector this way, I mean, you are saying that you can, you know how the Fuchsian group elements are parameters in terms of L and P, right?
Yeah.
So suppose you change A to A plus delta L,
Yeah.
okay, then that will change the parameterization, that is the level of the Fuchsian group,
Yeah.
which means that the identification across those boundaries will change, right?
Yeah.
So from that one can construct a measure, right? I mean, you just look at the new coordinates in terms of the old coordinates,
Yeah.
okay, and convolute with B and B bar.
That is true, but
So why not construct a measure that way?
so the point is that to construct a Fuchsian group corresponding to a specific point on the Teichmuller space is possible, but it's not that easy. There exists a systematic algorithm. That's the only thing.
Okay, yeah.
For
So
gen-
suppose you follow that systematic algorithm, you are saying that that doesn't
It-
lead to a
It won't. It's actually it's actually not tractable. It's extremely complicated. Even the algorithm, if you are really interested in getting a particular Fuchsian group for a specific surface, say lower genus surface, you can do that. When it's a lot of work, but it's not that hard from the conceptual point of view. But to use that for constructing the tangent vector, it seems hopeless for me. It doesn't look so smart. It's very hard to follow that.
Because to me it would think that, I mean, if you know the correct transformation, right? Once you know the Fuchsian group element,
Yeah.
you know how the D plane, the upper half plane is identified, right?
Yeah. Yeah.
Now you change the parameter a little bit,
Yeah.
you have a new identification,
Yeah.
right?
Yeah.
And then you express the earlier identification in terms of new one, and that should generate the tangent vector.
That is true. That is
So
true.
That's not wrong.
Actually, so here I am dealing with a general Fuchsian group, and then I mean the construction which provides me the Fuchsian group representation is not that straightforward. It's an algorithmic prescription. So you start from some lower genus surface, a pair of fans, construct the Fuchsian group, then glue them to get the 4 holes here, then identify some of the boundaries to get torus with 1 volt. It's a systematic procedure. It's an algorithmic procedure. So I think it's very hard to follow that to construct some tangent vector. So this looks, this is so simple, right? Once you know all the other details.
Yeah, it's so simple, but the point is that this introduces non-holomorphic quantities, right? Whereas in the other way of doing it, it's all holomorphic.
Why it's holomorphic in the other way?
Because across those lines, I mean, you have, suppose you have V as a function of W,
Yeah.
right, across that line,
Yeah.
and then you have V as a default function of W,
Yeah.
okay? Because function has scale.
Yeah.
So then you have to express f of W in terms of f tilde of W,
Yeah.
right?
Yeah.
It's still an analytic transformation. Local. It's locally analytic. Then
Yeah.
of course it's not global analytic, and that's what you integrate.
Yeah.
You convolute multiply by V and integrate.
Yeah.
right?
Yeah.
So you get the another contour integral around those surfaces, those boundary curves.
Yeah. So here also actually you are reproducing the same thing, right? So the
Yeah, except that you are integrating, doing a 2-dimensional integral instead of a 1-dimensional integral.
That is
Like,
true.
You really integrate the Beltrami over 2-dimensional.
so you can so this expression looks complicated, but you see that there is a sum over images, and then this sum over images can be used to convert the domains over which I am supposed to integrate. I am supposed to integrate this over a Riemann surface, right? Now I can
Yeah.
absorb some of this sum to the integration and make it into a integration over a column.
Okay, but here you really have an integration over a car, not even about a column.
Yeah,
Right?
that is true.
In the-
And then that is true. And then what one can do is you can analyze this integration over caller and then convert into a integration over line.
I see. Okay.
So at then you will get the same thing. So
Okay.
to me it looks like here we have lots of, we have control over the thing.
Okay. So, thanks.
So through this I just constructed any tangent vector that corresponds to a twist transformation. Now I haven't constructed what is the tangent vector that corresponds to a length variation, del by del L, because Fenchel-Nielsen twist is not directly varying the lengths of the curve. It's actually performing a twist. At the end that has an effect, but the twist transformation, this idea is very hard to use for constructing the tangent vector that corresponds to del by del L. So here what one can do is you have to use the Weil-Petersson geometry of moduli space. So far I just said that I have some nice construction of Teichmuller space and I know what is the parameterization. I didn't tell you anything about the geometry. I didn't tell you what is a metric on that space that I constructed. This is just a manifold, right, which has dimension 6h minus 6 plus n. Now I should be able to define a metric on it. We can do the. Yeah. Yeah.
How many parameters are related to the space of the curve?
0.
0.
Yeah, if I fix the boundary length.
No, no. I mean, but those are also parameters.
Yeah, in that sense 3, right. Yeah.
Now, when you glue them together,
Yeah.
how many do you have?
So I have 3h minus 3 plus n.
So you have
Into 2.
sum of the two,
Yeah.
which is
Yeah.
6,
Yeah.
and in addition, and something else.
Yeah, and the twist, right. Yeah.
So you don't have 6, but you identify 2.
Yeah, that's true. Some of them you identify.
So suppose you want to do one gauge. These two lengths have to be the
Yeah,
same.
that's what I want to see if it matches. So it's with the other ones it's just 6,
And these are-
they have the 4 lengths and whatever.
And the
this
intermediate-
length which is the same on both
Same,
sides. So that's
exactly.
fine.
No, yeah, but
And then what?
if you don't think about how you're doing it, you just look at this, that what you have 4.
No, you are not allowed to glue two boundaries which have different lengths.
You have to.
No, but I'm just counting, I have the final object.
Yeah.
Something that has 4
Yeah.
boundaries.
Yeah.
And I want to know how many parameters.
Yeah, so the counting is easy if I start from the full Riemann surface and then just cut it, right? Then I know how many locations are there.
Which is, I mean,
That
that's
would
a
have six.
number, I want to know the number.
That would have
Yeah.
Because it has to be,
It would have 6 because
it would have 6, then it matches, as you say.
Yeah.
Because it's the 3 plus 3, but you have to remove one of the 3.
One of the
so they
three.
have to be equal, and then the 2
Twist, yeah,
gives you the extra parameter.
That is
Okay,
true,
that's
yeah.
what I wanted to do.
yeah, yeah,
to see that it has 6, you notice that if those 4 things were just points,
Yeah.
not holes, then it has 2.
2, exactly.
Because it's one complex. Okay, and then the broadening of each of those is possible.
That's true. So now there is some classic result by Wolpert. I don't think I have to go through that detail. So maybe I can just immediately state. So
So it's one more elementary question.
yeah,
Along those lines. You said you could get every Riemann surface by gluing together these pair of pads, which lets L1, L2,
yeah,
L3.
yeah, yeah.
So for instance, if I wanted to get genus 2 Riemann surface,
Yeah, yeah, yeah.
would I would glue together 2 of them
Yeah, that's true.
and
Identify.
and match them up,
Yeah.
right? Now, is there a one-to-one mapping between L1, L2, L3, and 3 twists and the surface you get?
No,
No.
it's not
So you-
one to one.
So you can get the same surface in many different
Many
ways.
different ways. That's why I have this redundancy of MCG still there. Mapping class group is still there. So what I have is just Teichmuller space. I'm not obtaining the moduli space. So that's the second problem which we know how to solve.
Yeah, continuous I think just the number of parameters match.
Yeah, yeah. It's not continuous. It's a discrete group, just like SL2C in the case of torus.
I see. But it's exactly the mapping class group. The only ambiguity is mapping class.
Exactly the mapping class group.
Okay, so up to mapping class group, there's a unique way of
Getting Riemann surface.
getting Riemann.
Yeah,
So this is a very nice parameterization, which
Yeah.
you then have to model out by.
mapping class group, right.
Hey, in Kulchinsky, I read about this thing called the plumbing fixture.
Yeah.
It sounds sort of similar,
It's sort of similar, but
but you have to put in cubes in the middle.
middle, yeah.
You don't have that here because you're varying the lengths of these.
Yeah,
Is
yeah,
that's
yeah,
the
that
difference.
is the difference.
The
So-
plumbing fixture has a fixed length.
Yeah, so when I try to construct closed string field theory using this hyperbolic surface, I had to really, compare this Plumpin fixture construction, which is the string propagator, the usual string propagator, with this Fenchel-Nielsen gluing. So what I saw is that, it looks like Plumpin fixture construction and the gluing construction is almost same, but they are actually different. So that, you can't really think of this gluing as string propagator. You have to do some slight modification, which I could do, and that's how I constructed the closed string field theory using this hyperbolic surfaces.
But he's using the length of the curve here, which is the length of the column.
Yeah. So approximately, say you have this Plumpin fixture parameter t, right, which is like a complex parameter, which I can write as e raised to I theta plus s, right? So we have this Plumpin fixture parameter. Now what we have here is length and twist parameter. So you would love to know, say when length is very small, where you have a long hyperbolic cylinder, which looks almost like a hyperbolic cylinder, and in the other case, when t is very small, when you have long cylinders there also, right? Now it's interesting to see what is the relation between L tau and this Plumpin fixture parameter. So the relation looks like e raised to minus 2 pi square L plus I 2 pi tau by L. So there is actually a relation, but still it's sort of a fake relation.
And was it right? Do I remember right that the plumbing fixture construction you couldn't get in? There was regions
Yeah,
like
yeah.
that were left out.
Exactly, yeah.
Here there's nothing left out.
There is nothing left out. So that's the main difference, and that's why I feel that maybe using this Plumpin this gluing construction, if there is if there is some mathematical result, it might be possible to construct full closed string theory using just bicubic action.
I see. The regions that were left out were new vertices.
Yeah,
Plumpin.
Plumpin fixture. Here nothing is left out.
I see.
So it is highly possible that you may get a cubic closed string theory.
I get it.
Cubic is related to the pair of lines.
Yeah, pair of lines. So the pair of line itself may act like a fundamental vertex, which could build any amplitude, provided everything properly matches. So there are some more things. So the measure part looks like it's localized around the gluing, right? So that looks like it's nice, a nice thing. So that measure part will provide appropriate B mode for constructing a string propagator. And then the CFT correlations, definitely you can split into different pair of fans. So that also goes, you can split. Now the whole difficulty is, here I am performing an integration over Teichmuller space. Whether the Teichmuller space, I'm not supposed to integrate over a Teichmuller space. I'm supposed to integrate over a mapping, modeless space, right? Mod out by MCG. So somehow I will find a way and then convert the whole integration over moduli space into Teichmuller space. And then to do that lifting, I have to multiply every string amplitude with some weighting factor. And then whether that weighting factor splits or not. If that weighting factor splits, then splits into each pair of fans. Right? So that it splits into different vertices. If that weighting factor splits into different vertices, that means I have cubic string field. So that's why I have a precise mathematical problem which a mathematician can solve. And then if he solves that means I have a cubic string field theory. There is no reason to believe that it's impossible. There is no such identity. Maybe that no one knows. And if somebody says that, come up with a no-go theorem that you can't ever produce such an identity, that means you won't be able to get a cubic string field theory.
Degrees about getting the
mapping class group, right?
Yeah. Okay, Rohit, there is a general argument by Sonoda and Zoibak,
Yeah.
which claim that you cannot construct cubic
That is true.
closed
So the general argument uses the fact that their propagator is coming from plumping fixture.
Well, the propagator is 1 over L0, right?
That's true.
L0 plus L.
Yeah.
That is still true. I mean, that will be true even in your case, right? The propagator
It's
in
not.
your case will not be 1 over L0 plus L0 plus.
It's not. It may not be that simple. Because I mean, you see in the case of plumping fixture, you could do the
Yeah.
state operator mapping in an easy way, right?
Yeah.
So here, what I'm having is a boundary, right? So I have to insert an appropriate wave function on the boundary.
Yeah. But the gluing, I mean, ultimately, when you, I mean, suppose you have a cubic string field,
Yeah,
right?
yeah.
Then part of the 4-point amplitude will be from the Feynman diagram.
That is true. Yeah,
I mean, all of the 4-point amplitude.
Yeah,
right, will be
yeah.
from the Feynman diagram.
that is true.
So I would have thought that that propagator that we are using
Yeah.
will still be 1 over L0 plus L0, right? Or it's not true?
No, it's not true. Actually, I have to redefine my propagator, which I don't know what exactly is my propagator. I haven't even tried it because I don't know whether such a mathematical result is available or not. Maybe I will discuss with you. I mean,
But yeah, I mean, can we just check even for a 4-point? Suppose you have to reproduce a 4-point.
Yeah.
Forget about higher point.
yeah,
3-level 4-point function.
yeah.
Yeah. Whether such a thing is possible, right? There it should be at least easy to settle.
That is true. It should be easy to settle. Yeah.
Because if I remember correctly, they claimed even the 4-point function cannot be gotten from
Yeah.
purely cubic one.
So actually, I discussed this with Barton, and then
Yeah.
I mean the main thing is that whether I am using his kind of propagator. Am I using plumbing fixture or sewing to get the propagator or not? So I have to really definitely change that sewing. So I have to use this gluing procedure, the cutting procedure. With that cutting procedure, I mean the point is that if I write down elementary interaction in clustering field theory following Barton's procedure and with this new construction, I see that it looks like elementary interaction itself is coming from some sort of cubic interaction. I mean everything looks like cubic, but there are small obstructions.
Okay.
If you do an analytic transformation, suppose you've got, let's say, cubic, some action with a propagator and some polynomial term.
Yeah,
Then you do a polynomial field redefinition.
yeah,
The propagator will not change.
yeah, yeah.
You'd have to do something non-analytic for the propagator.
Yeah.
So maybe you're suggesting that your field, that the fields in your procedure
Yeah.
are related to the fields in some other procedure by
Yeah.
a non-analytic.
Non-analytic field redefinition. Yeah, it might be.
But
It might.
depends on the QB then, right?
Yeah.
If it's having QB size, okay, no
Mm,
problem.
yeah.
Then
Sure, yeah, yeah. Mm. Yeah.
So what is the statement?
Yeah, that the fact that then it's not the psi, you don't start with a kinetic term that is psi q psi.
Yeah, yeah. I should not start with that. With that, if I start with psi q psi, then definitely I won't be able to produce cubic string field theory. So it's again I'm using the plumping fixture procedure.
Yeah.
So there is a mismatch
Maybe-
between.
Yeah, that will be the first thing to settle. That what
Exactly.
kind of kinetic term we should have.
Yeah, I just started analyzing it. I think I will discuss with you. That's why I told you I
Okay.
wanted to discuss. Yeah. So in case for a moment I can forget the fact that I mean whether the mathematical result that I require is existing or not, I can just forget, and I can look into the remaining pieces and see whether I can get a cubic kind of structure. So it takes you to a situation where you are actually settling. I mean, at least you are asking a concrete problem or concrete question. Can you solve this particular question or not? If you can solve it, then you can get a cubic string field theory. If you can't solve it, then I don't think it is possible to get a cubic string field theory. Yeah, those issues. Open string case, I mean, I haven't studied their structure. For the open string case, I think you don't have to really worry about the mapping class group. They are not that non-trivial as this.
But everything can be made local.
Yeah, you can and you can get everything from cubic action because you can reproduce a full moduli space of open strings by just by using cubic lattices.
It's a very complicated way of designing classification.
In this case, the explanation
But
mentioned
I'm
has to
saying
do with the mapping transformation.
Yeah, 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 yeah.
Using this computation
To the Teichmüller space.
model space to
Teichmüller
Yeah,
space.
it's the calculation of
But
the
if there is a similar equation, how is that got passed?
That actually the issue about mapping class group itself is not there in the
Is not there.
not there in the open string case.
So the open surfaces, they don't have
Complicated.
large isomorphism.
Yeah.
No, they don't. So they are easy to handle. They are easy to handle. Or in other sense, the plumpy fixture that you do in open string case matches with this kind of gluing procedure. So you see, the plumpy fixture that you are supposed to do for a closed string case is more or less like a Mobius transformation, right? Because tau is a complex parameter, right? The transformation that you are doing is Cw equal to T. So that means C is mapping to T by W. This is like a complex transformation, right? But for the case of open string, this tau itself is real. So that you could think of the gluing itself is a spontaneous fixture.
Rohit, sorry, just in the interest of getting lunch, we should end up in
Yeah, sure.
in about 5 minutes.
Yeah, I will do that.
So,
So I think I almost said the thing. I mean, I could have done things in a more concrete way, but these were the ideas that I wanted to do. I mean, I can construct explicitly the Beltrami, I mean, the tangent vectors at a particular point on the Teichmüller space. This is something which I need for defining the string measure, which I did. And then I am saying that if you want to perform an integration over the moduli space, you can utilize the Fenchel-Nielsen coordinates, and then you start with the by stating that your integration is over the moduli space, and then I can find a decomposition of identity which has the following property. So the decomposition of identity with some black box here, there are some functions which I have to use. That's actually a sum over all elements in the MCG. So I have to multiply this, insert this decomposition of identity, and then multiply it with the measure
you
factor
can find the decomposition of identity in terms of tau.
in terms of tau and n. And then I just absorb that and then convert this into an integration over Teichmüller space with this weight factor here, multiplied with the measure. So that's why I am converting a string theory calculation into, I mean, from moduli space to Teichmüller space calculation. So it's more or less like saying that developing string theory on the Teichmüller space, not on the moduli space. So the differential form I am constructing is actually on the Teichmüller space, not on the moduli space, and then integrate it. So I can use this similar idea to construct string field theory. So that string field theory is constructed in Teichmüller space, not in moduli space. So the good thing is that now what is Teichmüller space? Teichmüller space integration is just integral over dl running from 0 to infinity and t tau running from minus infinity to infinity. So these are more or less like field theory kind of calculations.
Like in the top equation there, each region contributed equally?
Here?
Yeah.
No.
No. Wait, which was the string theory? There is a string theory answer which is only over
Moduli space.
moduli.
So that is the FH A1 to AN, right?
Yes.
And then I could, so actually this is sum with some, there is a sum over all possible cubic graphs that I can have. So for the case of 4-point function, I could look into the 4-point amplitude for the closed string case. And then what I am saying is that if once I insert all this identity, this calculation splits into 3. That corresponds to S channel, T channel, U channel.
Wait, first just, in string theory you're supposed to integrate over a fundamental domain.
Fundamental domain.
Now you extend that into the
Whole thing.
by doing identical integrations in each different fundamental.
No. Because if I do that, then I will get infinity, right?
Yes.
So the factor that I am inserting here has appropriate decaying property. So that although I am integrating through an infinite cover, I am kind of compensating with a decaying factor.
So what I haven't understood is how you know that what you do get with this is the same as the string theory.
because it's just, I mean, I can think of this as an integration over moduli space, and then here I have sum over MCG, right? And anyway, the string measure is invariant in MCG, so that I can just insert here and then take it outside.
And that is something that integrates to one.
Yeah, integrates to one.
I see.
Yeah. So that's the reason. There is nothing wrong with it. So what you are doing is you are actually decomposing.
It's like taking each region and weighting with different factors.
Exactly.
Some of the weights is one.
Exactly. Yeah.
Using one as the geometry.
Yeah. And that weighting has a nice feature. The nice feature is that if I'm
So you choose a particular fundamental domain as special because you break translation.
yeah, actually that has a interesting feature. So you see, if I look into the degeneration S channel, T channel, U channel, that corresponds to different regions in the Teichmüller space or the moduli space, right? So what it does is that this weighting factor do a nice thing. When I am integrating over a region inside the moduli space that is very near to one of the boundary that corresponds to S channel, then only that piece contributes. All other pieces 0, almost 0.
Right.
So you are actually decomposing your string amplitude and taking it back to field theory. So that's why it's very, I mean, is natural for getting a string field theory.
Okay, so yeah, I will follow that. So that in this language,
Yeah.
a given degeneration
Yeah.
will appear infinite number of times, right?
Infinite number of
Because it has
times,
infinite number of events.
infinite number of times with some weight factor. That weight factor is
Yeah,
like
with some weight factor, exactly.
that weight factor
Yeah.
is like exponential decay.
So you are saying only one domain will contribute to the weight factor and the
Yeah.
others will not contribute.
Others will not contribute when I go to the degeneration region.
So the weight factor depends on your kinematics.
It won't depend on the kinematics. It just depends on your moduli parameters.
So then infinite decay with decay with what parameter?
With the length parameter.
Oh, so the weight factor depends on where you are moduli.
Exactly. Yeah. It doesn't depend on any kinematic factor in Teichmüller space.
So do you expect these weight factors, so there are fundamental regions, right?
Yeah.
And then there is some coefficient here deciding.
Yeah, yeah, yeah.
Do you expect coefficient to move it?
That's the kind of mathematical result I want. The known identities by Mirzakhani and Makshain, and then there are some other identity by Lu and Tan, doesn't seem to have that kind of nice symmetry factor. So, but the point is that initially people were thinking that maybe whatever Mirzakhani and Makshain got might be a unique identity. Then people realized that there is a systematic procedure for constructing all similar kind of identities. You see, the reason is that we are looking into hyperbolic Riemann surface, which is a highly symmetric surface. So it's natural that they will satisfy a huge amount of identities, and that is what they uncovered.
What is roughly their identity?
So I can write down their identity. So it's actually very simple. So for the case of one puncture torus, it's extremely simple. So for one puncture torus, what this identity says is the following. So I have to consider a closed geodesic on the torus, and then let's denote the length of that. So let me denote that color that particular geodesic by gamma, and then the length of that gamma I denote by L gamma. So then the summation says that you have to sum a function 1 by 2 by 1 plus e raised to L gamma, and I am supposed to take all the MCG images of L gamma, which is not a dentist. I don't want to include all those MCG transformation which will fix the curve itself, right? So dentist is something which will fix the curve. So I don't want to include those kind of elements. Otherwise, I mean, if I include, then that will make it infinite. So I am supposed to sum over only those MCG elements of torus 1 divided by the dentist with respect to gamma. This is equal to, and H belongs to this group. This is equal to 1. This is the identity. And it looks surprisingly simple identity. you see, you can use this identity to compute the volume of moduli space of one punctured sphere. We know that with a lot of work one
Yeah,
can.
Roji, can you just read out? I didn't. So it's what?
I can write it
Two over-
bigger. I can write it bigger.
Yeah, I can understand the sum,
Yeah.
but yeah,
1 by,
yeah.
it's actually 2 by 1 plus e raised to L h dot gamma. H dot gamma means I take curve gamma and take a MCG image
I see.
and then compute its length and then sum over all h that belongs to MCG of torus divided by den twist that I perform with respect to gamma. So see, you can see that when I take L goes to infinity limit, so this whole thing is going to give me a huge contribution, right? No, it's not very less contribution. It's exponentially suppressed. When I take L goes to 0, this is the one which is dominating. It's almost 1 order of 1 contribution. So that's the
So when you go to 0.
yeah. When I take L goes to 0, it has
Yeah.
it has maximum contribution.
But yeah, but what about the images? Images don't contribute.
So now I can use this identity to compute the volume of the moduli space.
Oh, I see.
Yeah. So
I think only one gamma contributes.
yeah. So let me write it. So d tau into dl is the volume form for the moduli space of torus with one function m11. So this is the integral that I am supposed to perform. This is the volume form on the moduli space. So and then this will give me volume of torus moduli space of torus with one function. But unfortunately, I don't know what region of tau 1 L corresponds to the moduli space. So what I will do is I will just insert this identity. And this identity, once I insert, I can sum the I can combine the identity the summation and the integration to obtain an integration that runs from
The whole time.
0 to infinity, not whole Teichmuller space. If I want whole Teichmuller space, I can use a identity for den twist also, which is actually a trivial identity.
Okay.
And then I am supposed to integrate dl d tau multiplied with 2 1 by e raised to L. So this is a simple integral, and tau is I am supposed to integrate tau from 0 to L because I don't want full den twist.
Yeah. Okay.
And then 0 to infinity. So this gives me 0 to infinity L 2L dl divided by 1 plus e raised to L, which is just pi square by 6. This is the volume of Teichmuller space, moduli space of one puncture torus. Now if I want to use the same Fenchel-Nielsen coordinate and then somehow compute the volume by finding the fundamental domain, it itself is a paper.
Wait, sorry, yeah. You probably said this, but I missed it.
Yeah.
In the limit that L goes to 0,
Yeah.
we're in a very special kind of torus.
Yeah.
In that limit, you get maximum contribution when this guy is the 0 element curve.
Yeah. Yeah.
But the other guy, is it infinitely suppressed compared to this contribution?
Yeah. Yeah.
Why?
Infinitely.
Has to go at least once around the other.
Yeah.
The
Yeah.
other guy? And
So
that
see.
ratio is infinite.
Yeah. So that's a nice property of hyperbolic surface. If I degenerate, other circle will.
Are we working in convention where the smallest length is 1?
Smallest length is no. It's actually not period matrices. These are genuine lengths.
Okay, so the other guy goes around
So if I have a collar which has very small length, then the geodesic that crosses through that collar will have infinite length. This is guaranteed.
Yeah.
But I'm not understanding. So if I take this to 0, L goes to 0, I get 2 over 1. So that's 2. If I take the other guy, I get
2 over 2. 2 over 2.
2 over 2. Fine. Then I get 2 over 1 plus e to the power L,
Yeah.
where I can think of that as finite and this guy being 0.
Yeah.
So don't you need some normalization for your L?
No.
I'm not understanding.
We're
See.
using the hyperbolic metric, right?
Yeah. So surface.
We're using the hyperbolic metric to measure L.
Exactly. So I already fixed that by saying that the
So
metric has curvature minus 1.
Torus, this is not well
Close to the point.
With a puncture I can do it.
Torus will-
with the function.
Puncture. Yeah.
So the statement is if L goes to 0, then every other image of L
Yeah.
has infinite.
Infinite length, so that they will contribute very less.
And in the limit it contributes.
Exactly. Yeah.
I see. Oh, thank you.
So So if I this thing will be more clear if I use the identity for sphere with 4 punctures. Then one can easily see that. So there is an analogous identity. That identity says that the answer will split into S channel, T channel, U channel. And if I go higher point, then the amplitude will split into associahedron. All 3 puncture, all cubic graph will contribute.
So what is the problem? I mean, why can't you just use the identity?
So this identity won't have enough symmetry.
Symmetry.
Yeah. So the point is that you are even the loop, you are thinking of like integration over some closed geodesic, right? You don't have any loop integration in that sense. That's why it's always cubic. So if here, right? In this case, right? So in this case, always so your parameter is localized here. So you don't have any parameter running like this. No, nothing. Yeah.
What did you say about not having symmetry?
So you see, actually, I wrote down a identity for a 1 puncture sphere. So I can write down similar identity for a Riemann surface with finite boundary length, and then that formula picks a particular boundary to write down. So I have to choose a particular boundary, and then I say that the whole sum will sum to that the length of that particular boundary. So that is a highly non-symmetric identity.
But for your purposes, you don't need a surface boundary.
But when I try to integrate, so you see there are so many Fenchel-Nielsen coordinates corresponding to boundaries corresponding to geodesy having finite length, right? So the point is that the identity of this kind. So the particular identity I am mentioning is the identity by Mirzakhani, and she used this identity for studying moduli space. And then what she did is that she found a recursion relation for the volume of the moduli space. Now one can somehow that it is possible to argue due to the work of Wolpert that this volume contains the information about the intersection numbers that you have, that you can define using the non-trivial cycles in the moduli space. And then she showed that they satisfy all this Virasoro kind of recursion, which she proved that the intersection numbers in the moduli space satisfy recursion relation. Intersection numbers from the point of view of topological gravity means they have just correlation function of topological gravity. So what she did is, using this simple nice identities, she could find a surprising proof for Cohn-Shewitz-Witten conjecture. So this is what I am using. So what I expect is that when I take field theory limit, it may provide us some new identities, new recursions for field theory amplitude. It may. So you can use this formulation of string theory to study some new aspect of field theory. Or if I get an appropriate identity, we can try whether a cubic string field theory itself is possible or not. So that's the thing that I wanted to say.